Okay, well, now let me remind you where we were at last time. Let's see, we talked about, so we're talking about condensed phase, and we're just doing the simplest thing possible. We're just pouring liquid A into liquid B, and I'll make that water and ethanol because that's funny. It's also a really good example. A lot of the nuances of the thermodynamics of mixing two things together, fun as that is, a water ethanol system actually displays a lot of the traits that you would want to talk about. So that's nice. Now recall that we started out with, oh God, I gotta see, I'm doing it again. My symbologies, I have to try to stick with the symbologies. That we have these excess, so this is called an excess function. And recall what this is. This is the volume of the solution. So this is my water ethanol solution. And this is the volume of the water and ethanol before they mixed. So it's kind of brainless, right? You understand that. I did mention, though, that, and I'm going to make a little generic multi-component thing here, but I never do more than just A and B. I never do more than water and ethanol. I mean, I could do water, ethanol, and ethanol or something, but I won't. That's kind of weird. Okay, now recall that this is the volume per mole in the mixed state. That's why it gets a little hat. And that is just the regular volume per mole. That's the 18 mils per mole of water. That's the unmixed state. Okay, so this is an excess function. And remember that we have the same for Gibbs energy, and it's boring. I'm just going to write the same thing, except a G instead of a D. Except I put it the B there. And there's not much to this. Now, there's a little bit of a nuance to this, which is kind of interesting, which is that these are just pure changes. So we always talk about changing thermodynamic variables, but this is like a change of a change, right? Because excess functions are like the change of a change. So there's a little nuance to it. It doesn't really matter that much in terms of really working problems because it all comes down to the same old of, let's see, delta G is everything because we're in a constant temperature pressure world. So that'll be 25 degrees. Okay, so while these are excess functions, if you totally forget that and work the test and homework problems, you're going to be totally fine. So not a big deal. It's just, this is kind of neat. This is, if things, well, let's say things didn't mix and you just put A and B together, if you put water and ethanol together, their G content would be exactly the same. But that's not reality. Reality is things mix. And when they mix, they affect each other. And such that they can have different volumes, and that's not so important. They can have different G, G energy, just call it that, you know what I mean, Gibbs energy, and that's hugely important. Okay, so now this is where I was at before. I have to admit I'm a little flummoxed just because it's been rough. Let's see, now I showed you a little bit about how this, I kind of cut to the end where I pointed out how you can get really complex behavior if the entropy is like negative in the case of diethylamine and water, and how these two can play this weird game with each other, so just recall that. But then again, that was cutting to the end. Let's back off and not study such a complex situation. Let's do something real simple, which we'll call the ideal case. And what I need to do is then, under an ideal case, an ideal solution, which will mix, it'll just mix. What we came up with was, we actually started analyzing the vapors that are in equilibrium with the liquid. So recall that I started out explaining like, okay, I got a cup of water, it's a dry room, I just put the cup of water there and it will evaporate to the tune of about 3,200 pascals. That's way less than the 101,000 pascals that's atmospheric pressure, but then again, my atmosphere isn't made of pure water. It would be if I was SpongeBob, but No, there's plenty of water in the atmosphere, but it's not pure water, right? So a cup of water evaporates water out till it's at 3,200 psi. Now, if I had mixed in some ethanol, what happens is the ethanol evaporates too, and it actually ends up taking up some of water's position in the atmosphere. So, so what we did was we started thinking about how those vapors mix. Now remember, I'm using the word vapor as opposed to gas. The reason for that is I want that to conjure up the image of the gas that comes off a liquid. Now, gas is gas, vapor is gas, it's all the same. But when I say the word vapor, I'm going to use that exclusively to remind you that I'm really going to think, I'm talking about gas that came from a liquid pool somewhere, and so I'm really more concerned with the liquid than the gas. Okay, regardless, so I had a solution of water and ethanol, and they both evaporated, and I calculated how do the vapors mix, and A will be water, and B will be ethanol, and because now remember, whenever I derive anything, when I talk about the thermodynamics of like water, you have to then just tack on the same thing twice, just knowing that the other part's the ethanol part, right? So okay, so what I get from this is, recall that this is really quite simple. This is what we did for reactive gases. At one point, we talked about how if you're going to get a gas phase reaction, they have to mix, and that perturbs the Gibbs content. This is the exact same thing. 100% the exact same thing. It's just that they're not going to react. In fact, sometimes I actually cover this part before I do reactive gases, because this part is actually the same thing except simpler, because there won't be a reaction. Negative to that, though, is the fact that I'm in the condensed phase. I'm technically talking about solutions. So I never know whether I should be doing this first and then talk about reactions, or what I'm doing with you guys, which is the opposite. But anyway, but here we are. All right. Now there is a slight change. So remember that this is actually the work. This is the work of gases expanding into each other's space. We know that it's a reversible work. We know that reversible work is the thing that's delta G. Delta G is equal to reversible work. So there you go. It's just in pressure form. The initial pressure, when we did reactions, the initial pressure was 1 bar. And that was because that's just our thermodynamic standard state. I can't do that in this case. That's not going to work, because when I open up a cup of water and it infiltrates the atmosphere, it will not reach a partial pressure of 1 bar, because then I'm under the ocean. So I have to be kind of realistic here. The pure partial pressure, that gets a little star. The pure partial pressure will be, I open up water in a dry room. What is the water content at equilibrium? The answer is 3,200 3,200 pascals. And again, that's about 3%. All right, the atmospheric pressure is 101,000 pascals. Okay. So anyway, and then the partial pressure in the final state is just water. So instead of opening up a cup of water, this is a mixed drink. And what I'll find is that the partial pressure of water is likely less than 3,200 psi. 3,200 pascals. It's less because ethanol took up some of its space. So I measure the partial pressure of water, and there you go. And again, I have to tack on the same with ethanol. Now we know that G's per mole are chemical potentials. And so that's more important. And what we end up with is, again, I keep screwing this up. RT, there we go, I'll remember this. I'm doing a little algebra. So we find this chi-A ln chi-A plus chi-B ln chi-B shows up. Wait, sorry. Made a mistake. I jumped one step ahead in this derivation. My bad. I'm just writing the pressures again. Sorry about that. Now you know where I'm going in the next step. And I even talked about this a little bit last class. Okay. All right, so there you go. All right, and now I also mentioned at this point, I'm still reviewing, that whatever happens with the vapor happens to the liquid too. So the trick here is to hijack the changing chemical potentials of the vapor, which is a gas, and God knows we know what gases do. We have beaten that up to death in this class. We know all the thermodynamics of gases doing this or that. There's nothing gases can't do that we can't calculate. In this case, they mix, they change their chemical potential. But because we assume it's at equilibrium, the damnedest thing is this is the same chemical potential change of the liquid. So cool, right? That's kind of neat. And it's simple because we've already covered this. This hopefully is kind of familiar to you. And sometimes, like if I've taken like a year off from teaching this class and I'm reviewing my notes and I'm like, yeah, wait, where does that come from? Again, it comes from the work. It's the work of the gases expanding into each other's space. That has, I mean, that's the definition of mixing. And yeah, so there you go. That's where it comes from. Okay, now this is where things kind of go off the rails. And this is where I'm going to insert an approximation that will carry through about half this class. And it's actually kind of hideous. Here's the problem. This is perfect. And it truly, I know it's perfect for a gas, and that I absolutely believe. And it is true for the liquid too, in terms of chemical potential. No approximation. However, how do I measure the partial pressure of a gas? Any of you know? It's kind of complicated. There's some tricks with water. You can actually use like certain chemicals that absorb water and change color. Anyway, there's some tricks. But measuring the partial pressure of vapors in our atmosphere is unfortunately a little on the difficult side. If you really want to do a good job with this, you have to use a mass spectrometer. And so that, of course, samples the air and tells you exactly what's in your air. Anyway, all right. Now, remember that this class was basically in the form, in 1930, the students in the class are hearing the same things that I'm saying to you right now. And they did not even have mass spectrometers, right? And even if we had a mass spectrometer, that damn thing is expensive, and I'm probably not going to use it to measure partial pressures of vapors from my mixed drink. Okay, so this is where Raoult, who was a French, yeah, I know he's French. Anyway, he was an electrochemist. And so understanding the thermodynamics of electrolytes is really important in electrochemistry. So he needed to know the delta G's of mixing and all that of electrolytes. And he's the guy who came up with a lot of this. But he needs a way to figure out what these are. And he has a simple idea. What if the partial pressure of A was equal to the mole fraction of A, and that's the mole fraction of A in solution, times the pure partial pressure of A. And again, now, remember that whatever I do for A, I do for B, and I just tack it on after the fact, right? So just, I'm sure that's sensible. You're used to that. Okay. Again, the guy says, if I have a cup of water, and in a dry room, and then I measure the partial pressure of water as 3,200 pascals, if I actually had a 50% solution of, so by mole, water and ethanol, then I would measure 1,600, half. I would measure half the partial pressure. So the pure partial pressure of water is 3,200, so in fact I'd measure 1,600 pascals. It would be half. And then the same for ethanol, and I'll tack that into this equation. And I'll just do that. So, and remember, this is what God, it's going to be one of those days. So I won't even do the algebra, but you can see that if I put in chi A, the mole fraction A, pure partial pressure here, you get, right, it's very simple. And it's kind of easy to, you know, I don't have to memorize equations, but if I did, this would be relatively easy. Okay. Now again, I want to emphasize this is hideously important and probably a explain in words question. This is the partial pressure of the vapor, and that is the mole fraction of the liquid. Now I hope that this kind of makes sense. It makes a lot of sense to me that if imagine like the surface of the solution. I walk into a room, a dry room with a cup of water. The reason that water vapor enters into the gas phase and it equilibrates at 3,200 pascals is because some water evaporated off the surface. But now, if I have a mixed drink, 50% ethanol, which would treat me just right, then some of that spot, right, the water has to come off the surface, but it's not all water on the surface. Some of it's ethanol. And that ethanol will fly off into the gas phase. It's quite good at that. And it takes water's spot. So, the partial pressure of water is going to go down by about as much as, probably sitting on the surface. That's where the vapor comes from, right? Sound good? Yeah, what do you think? Like, not a bad approximation. It's a hideous approximation. It's almost totally wrong. It depends. Some things this works quite well for. We're talking like toluene and benzene, which I don't know why you would mix those two together. They're basically the same thing. But then again, that's kind of the point. Water and ethanol, it doesn't work that well. No, not really. Now let me give you a hideous example. Hexane and water, oil and water, right? What do you think? Is that going to be about right? Let's say 50-50 hexane, 50-50 water. What do you think? How well does this work? Why is that? It's going to be dead wrong. And for a simple reason, hexane and water don't mix. All right, if I had a cup, if I poured in hexane into here, I'm not beyond drinking gasoline. What would be the partial pressure? Now again, I walk into a room with a solution. It's hexane and water. I measure the partial pressure of water vapor after equilibrium. What number do I measure? You should give me, now remember I told you the pure partial pressure is 3,200. Raoult's law says a 50-50 solution would be 1,600. But now I'm telling you, I'm walking in with hexane. Is hexane more or less dense than water?
More.
Less? People? Heavy oil is more dense, all right? But hexane comes from heavy oil. I know that's probably what you were thinking. Hexane sits on top. Okay, I walk into a dry room with a hexane water solution. I wait for it to equilibrate. What is the partial pressure of water?
None. You don't see it.
Zero. Right, it's zero. Because it can't evaporate because there's freaking hexane sitting on top of it. Right, so Raoult's, this is called Raoult's law. This is kind of Raoult's law. This is pretty important. You don't have to put a little star by that. But it can be hideously wrong. Like, and again, in the hexane water solution, if I have 50-50 hexane water, this will not work at all. I should be getting zero for my water. Oh, and I would get, for hexane, I would get 100%. Whatever its partial pressure is wouldn't be changed because it's floating on top. But also notice, why would any of this work? I'm trying to tell you about solutions, but these don't mix. So why would it work, right? So there you go. So now what you're seeing here is that we're going to have a range of behaviors. Raoult's law is going to work for things that mix and mix well. It will utterly fail for things that don't mix. And here's a little hint. There's in-betweens. Take ether and water. I'm a bit of a synthetic chemist. If you get dry ether from a stockroom, it's not dry ether. It's about 5% water. I'm sure it came from the factory dry, but in shipment, they just can't prevent water. Water is everywhere. It's insidious. Water can get through plastic. It just takes a while, but it does it. It absolutely does it. So by the time I get anhydrous, it's a joke to me. Synthetic chemists have known this for years. If I get anhydrous ether from my stockroom, it's 5% water. And I can know that by, I throw in a chip of sodium, and it reacts like crazy, right? Sodium doesn't react with ether, it does react with water. So anyway, it's after about 5% water in ether, it won't dissolve anymore. All right, so anyway, the point is that there's all kinds of behaviors and ranges of behavior. So for now we're going to work with this. We're going to work with Raoult's law. And we're going to talk about the best possible solution ever, things that absolutely mix. And then we'll talk about when they don't mix. Okay, now when it comes to Raoult's law, so Raoult's law in ideal solutions, let me write this down. Ideal solutions follow Raoult's Ideal solutions follow Raoult's law. Now, when I plug in Raoult's law into all this thermodynamic excess function, I'm going to find that everything should mix, given that they're ideal. So that's the point. Okay, now what makes an ideal solution? Now again, I'm going to talk about A and B, but I'm going to be mostly talking about like water and that. So I'm going to be talking about toluene or benzene, water or ethanol, or hexane and water. I'll always be talking about one of those, but this is going to be toluene and benzene. Okay. A and B have the same molecular volume. In other words, they're about the same molecule. Right, so like benzene and toluene, they're about the same. Or benzene, toluene and xylene, those are incredibly similar. Right? What's xylene? You don't know, do you? I think this is my grad students all the time. I'm like, oh, okay, well that's a quantum confinement effect. And they look at me and do this. I'm like, what's the quantum confinement effect? Anyway, okay, xylene is toluene with an extra methyl group. Okay, same molecular volume. Ethanol, propanol, about the same, right? Okay. Now what that means is though that units, anyway, it means that their mixing volume would be 0, their excess mixing volume. Now this is what I'm going to do to you on the test. If I add 1 liter of an ideal solution to 1 liter of another ideal solution, what's the mixing volume?
2 liters.
Fail, pass. It's 0. The resulting volume is 2, but the excess volume is 0. Right. So you heard that? You heard that? Yeah, that's an easy trap to fall into. If these things are ideal, because the volumes of the molecules themselves are basically equal, let's do benzene toluene. If I have a liter and another liter and I mix them together, I'm just going to have 2 liters. All right, but that's like not representing anything, right? Because I mean, I expect that. That's why the excess volume is in fact 0. The excess volume is the deviation from what you would expect. And there is none in that case. All right, anyway. Now, now you might want to remember this. A and B have same interactions. And you hopefully this is kind of an organic-y thing. So I'm talking about like benzene and toluene. How do those interact? They're like little pancakes, right? Right, they stack up. Little pi-pi interactions, right? Okay, ethanol, propanol. Those are probably, I'm not sure, I'm sure that's like an ideal solution. I don't know that off the top of my head. Hydrogen bonding. But now the reason water and ethanol is not so ideal is that water participates in 2 hydrogen bonds, and ethanol can only do 1. So that's why that's not so ideal. But ethanol, propanol, that'd be about the same, because each one participates in 1 hydrogen bond. So I bet those would have very similar interactions. Now what that would mean then is that the excess mixing internal energy is 0. Right. Now again, hopefully you've thought about molecules enough, mostly in organic class, that this hopefully is kind of sensible. Or office hours, if any of you ever felt like, what was that? Did you hear that?
It's the microphone.
Yeah.
Oh, that's so weird. Anyway, okay, stay away from there. So yeah, I hope it kind of makes sense, but now here's the point. Yeah, this kind of seems like, well, what the heck? Okay, well, so what? Just some stuff to memorize. Remember this? So remember, despite the funkiness with this excess stuff, H is U plus change in PV. But let's see, but pressure is constant. So this is P. So remember, we're at constant. Now hopefully you remember there should be another term here. Uh-oh, what have I got? What have I got? 0, 0. Right, the mixing excess enthalpy is 0. Now there's a funny way to understand this. If I mix benzene and toluene and I'm holding on to this, and I'm holding on to the cup and it's made of metal, what does it feel like? Hot or cold? No! Feels like nothing, right? It feels the same. Nothing has happened. Right, so actually a lot of things, hopefully that's kind of counterintuitive. A lot of salts in water that actually gets cold. And you know that there's cold packs when you play sports. So those are not ideal solutions. Water and ethanol, I think that actually gets warm slightly. Yeah, that one warms. You can't really presume to know. You want to measure these things. So, okay, but if they don't get hotter, warm or cold at all, then you've got yourself an ideal solution, and this would be why. Okay, now so what? Well, now again, remember we're following Raoult's law, and this is an ideal solution. It's going to follow Raoult's law. I've just defined an ideal solution, and now that I've got delta H's here, now I can go back to my delta G. And again, and by the way, hopefully some of you might be saying that this is even looking more and more like when we talked about gases mixing, and that's true because now I've wiped this out. So the mixing of an ideal solution, now remember, this is when things mix the best. Don't forget that. This is when things mix the best. Despite all these zeros, this is the best situation when it comes to mixing. And why the heck would I put two things together in the same pot anyway, right? Unless I wanted them to mix. And it is entirely entropic. Entirely an entropic process. Yes, minus. Let's see here. Entropy, of course, is going to be positive. I mean, that's brainless. Times minus T will be negative. Oh, don't forget, negative energies are good. That's the weird one. Negative energies are good. I know sometimes I'm like, oh wait, no, I've got a negative. That's not good. No, it is good, right? All right, so now what does this mean for entropy? Okay, S mix. And I will do this. I'm going to insert Raoult's law. So I've got minus. So don't forget that, and now see, I looked at my notes and I almost kind of did a double take. I thought my notes were wrong, because here's what happens. I got minus NAR LN let me tell you what I said. I almost did a double take. I freaked out because I'm like, where's the T? And there like where'd the T go? And I realized that, just look over here, delta X mix is delta G divided by minus T. So that's where the minus sign comes from, and then the T got wiped out. So now my notes are correct. Okay, now what we really want to do though is entropy per mole. So we do that by dividing by N, and that's because I'm going to want to put this back into the chemical potential, because that's more important. So I'll just rewrite this again. What did I do? Yeah, I messed up. I didn't get sorry and B. Sorry, you see what I did? Here, I'll show you. I had NA times Ka, but I didn't have my NB. So, right. The terms, whatever happens to A has to happen to B. They have to be the same thing, just without A's and B's, right? So, anyway, so I should have wrote this. Again, this is delta G just divided by minus T. And I'm just telling you that in general, we want to do this per mole. I switch back and forth. I know it may be a little annoying, but I do switch back and forth between doing per mole and not, just depending on what I feel like I'm talking about. Okay, and now remember that I use Raoult's law, delta G, and so I'm kind of inserting. Well, what I'm really just trying to do here is I'm trying to show that ideal solutions mix entirely by an entropic process. Okay. Now again, I almost did a double take when I was following my notes and I wrote this, because I felt like I was missing a T, but no, I'm not, because I divide delta G by T to get to entropy. The other thing was the minus sign. I'm like, no, this is positive. This is a positive thing. Why is there a minus sign there? Okay. I knew you guys were probably like all PO'd and like sick of me. Is pressure positive? Is volume positive? You see why? Okay, is R positive?
Yes.
Mole fraction?
Positive.
Negative. Right, there you go. There you go. Okay, now remember what happens if you're thinking, wait, natural log, is that positive or negative? Mole fractions vary between 0 and 1. Natural log of 0.5 is negative, right? If you get confused by that, plug it into your calculator. So positive, negative. Now I know that you have a sum here, but they multiply. They multiply. If you remember that negatives dominate. So it's net negative. It's net. We actually do it this way. But yeah, let me redefine my brackets so that they're also similar. Okay, this is net negative, net negative, net negative, net positive. There we go. There we go. So the minus sign doesn't need to be there, and it is, yeah, and it does work out correctly. Okay, so again, I want to summarize ideal solutions. This I will almost absolutely put on a explain in words. These are the identities of a ideal solution. I then take the delta G mixing that I had derived with Raoult's law, which is for ideal solutions, and I'm whittling that down to a purely entropic interaction, which is good. Entropy, remember, entropy is really in charge. Delta G is just a way to get to entropy. So the fact that I see this system entropy, I see the system entropy increasing is the best possible thing that can happen. And if you think like, oh, but what about the outside entropy? There is none. There's no change because the enthalpy is 0, right? Remember we talked about last time how mixing, I really like mixing because it really allows you to understand what delta G does. There's a system entropy increase or decrease, and an exterior entropy increase or decrease. The exterior experiences its entropy change by enthalpy. So in this case, where there is none, you only look at the system, and the system changes positive, so these things mix, for certain. Okay, last bit I want to cover is, there really isn't much more to this, but now that I've covered ideal solutions, I want to start, let me show you one of the, people often graph vapor pressure, and I even have data. I showed you some data in the textbook of vapor pressures from solutions. So again, these are vapors. These are vapors in equilibrium with their resulting solution. I'll have A and, again, I'll just always keep it down to just two things, A and B. Now, to know whether something is ideal or not, you really do need to look at the vapor pressures of the vapors, right, coming off the solution. And we want to do that as a function of concentration, because what we're looking for is, let's look at B first. So B has a pure partial pressure. And when I'm over here, I have a cup of B. I walk into a dry room with a cup of B and I measure the partial pressure, and I will measure the pure partial pressure. Because in all honesty, that's where that data comes from, doing exactly that. So I'm definitely here. But what I see from Raoult's law states that the partial pressure is the pure partial pressure times its mole fraction. So that's just a line, starting from 0. Okay, and then of course we would have the same for PA. There's no reason to say it would be the same value. So that would look like that. Remember that you have to make a little reflection. Remember, these are actually two graphs on top of each other. One for B, and then I just kind of flip it over and make one for A, but I just draw it on top of it. The mole fraction of A is 1 on the left because, of course, B is 0. All right, and then if I have a spectrometer that can measure the total pressure, it would just, the total partial pressure from these two is just the sum of them both. That's kind of brainless. Okay, all fine and good. But now things go off the rails. So let's go ahead, because I really have nothing else to say about this. The ideal solution is, to us, what a perfect gas was at the beginning of the class. This is the simplest case, so simple, there's really not much else to say. So let's go ahead and make this not happen. Let's go ahead and look at non-ideal solutions and figure out why we might see deviation from this. Oh, and again, don't forget that this belongs to A and that belongs to B. And you can figure that out based on how I label the x-axis. You can kind of figure it out. If I throw this graph at you and ask you to explain it, it's not hard to just re-engineer it. Okay, why would things go off the rails? Okay, let's think about the following situation. I've got a cup, and I will have little cubes, and that will be A, and I've got little circles of B. Now, what if the A flocks to the top? So it's like hexane in water. Not completely. It's not perfect. It's not perfect, but it's kind of obvious to me that there's a preference for A to float to the top. Now recall that B is trying to get to the vapor phase, but if I had a cup of B, all the stuff at the top would fly out to the vapor phase, but I see that A is kind of getting in the way. I'll draw a few more just to make it clear. And again, watch the video if you're not, my drawing skills are honestly bad today, but A is not helping. A is preventing B from going into the gas phase. So let me, giving myself some room here, let me redraw this and let me make a correction for what's obviously not quite right. Here I got to remember what pure partial pressure of B is. And normally this is what I just drew. This is the Raoult's law. Oh, it's not a perfect line and that bothers me. The word will blow up if I don't do it just right. Oh, and this line is tilted. Oh, there we go. Okay. Now, of course we're over here. We're on the left. We're on the left side because there's like a lot of A present. What I'm seeing here is that the vapor pressure, what do you think? Higher or lower than what I should get?
Lower.
Yes, lower. So what I'm thinking is going to happen is I'm going to see this kind of behavior. However, once the solution is nearly pure, I mean, it has to meet up with its pure partial pressure, if it's pure, right? Of course. So what we expect is this type of behavior. Kind of a downward bend, but it has to reconnect to, it has to go back to normal. Okay, now let me draw another limit to this. Now when I see this, I'm like, uh-oh, A and B do not get along. I don't know if it's their size or their interaction, but something about A and B, and that's why I drew squares and circles, they don't fit together like I'd want them to. And so that means that they're not ideal, and this is what would happen in the vapor pressure. And here, let me draw another case, and so you can probably guess what I'm going to draw. That A is kind of floating to the bottom. Now again, these guys don't really get along too well. I'll draw a little bit more. I should have drawn a little bit more A because B is the solute. B is the solute, A is the solvent when we're on the left side of the graph. Okay, it's not absolute, but when I look at this, it looks to me like A and B, they don't interact well, but in this case, maybe A is denser or something, and it's on the bottom, and it's like pushing B out. It's trying to kick it out of a solution. In which case, I'm going to be much more careful. In which case, instead of the Raoult's law result, you might expect this type of behavior. But again, it will asymptotically go back to, it'll go back to where it should go back to, because it has to, it's pure. Get our label axes, there we go. It will behave itself. Okay, so this is what we would call, in both cases, this is non-ideal. And so that's kind of brainless, you see from the molecular perspective. And notice that this one's kind of important. It's only happening for solutes, not solvents. Now, unfortunately, this is one of the things I don't like about this stuff. Solute is the thing you dissolve into the solvent. But now, in that example I harped on quite a bit of 50% water, 50% ethanol, which is the solute, which is the solvent? Neither. And both of them at the same time. Right? So this is nebulous, right? So typically, we know that a solute is the thing that gets added a little bit of, like salt and water. You just can't add that much salt and water, right? So, and that I understand, but there's other situations where it's not really clear what's a solvent and what's a solute. When you see this terminology, all that they mean is that your solvent is over here and your solute is more over here. And don't worry about the in-between. We'll actually talk about that on Monday. Okay, so when you don't see ideal solutions, it's because you see this deviation, but you only see the deviation, you see in both cases, you only see the deviation at low concentrations. And again, while it's arbitrary at what concentration do we label this thing a solute, whatever. Anyway, that's the point. Again, there's no, I'm not sitting up like, oh, there's no solution. Oh, wait, there's a solution. Here it is. No, there's no solution to this. What do you call a solvent? What do you call a solute? It's oddly a matter of opinion. The thing I don't like about this for PChem is that this is not supposed to be opinion class. Okay, now let me show you. Now this is the part I really hate. I hate this thing. It's called Henry's Law. Henry's Law. It's not a law, it's an approximation and a bad one. Okay, Henry's Law works like this. I'm actually going to redraw. I'm going to redraw that same thing I just did. This is in the book, by the way, and I actually have better figures than I can do here. Okay, Henry's Law is when you get this non-ideality. And what you do is, remember, let me remind you what Raoult says. That you basically have a linear function up into the pure partial pressure. So if the mole fraction is 1, then the partial pressure is the pure partial pressure. And that will always be true, because, I mean, damn. All right, but that's for a solvent. Right? If you're at a mole fraction of 1, that's a solvent because it's pure. Okay, what Henry's Law does is it redefines the pure partial pressure. So we don't call it that because it's not. We call it the letter K. So Henry's Law states that only for solutes that the partial pressure of B is its mole fraction times a constant, an empirical constant that just makes it work. It forces the relationship to work fine. And of course, if I had this behavior, this is unfortunately horribly difficult to draw. The Henry's Law constant is like up here. And I drew that hideously. It took me a lot of time to get it right in the textbook. I actually have this behavior drawn. You know, I was careful with like using Adobe Illustrator and MATLAB. But anyway, all Henry's Law is an empirical fix for Raoult's Law. Raoult's Law does not work very well. It only works for a couple of things. Only a few examples of ideal solutions exist. Most things are non-ideal. Their non-ideality shows up only in the dilute side, only on the left side of this. And so what you do is you say when something's dilute, I'll forget Raoult's law, I'll use Henry's law, which is just change the pure partial pressure into a number that works better. And you would know that from empirical data, just finding a number that makes it work. And that's Henry's law. And that's all there is to it. Now Henry's law ends up being relevant to gases dissolved in liquids. It ends up being relevant to that. And I'll work a problem. I have you do a Henry's law question in the homework, so I'm going to work an example problem. I know we need to take a break, but real quick, Henry's law is useful for only one thing, which is calculating the concentration of dissolved gases in liquids. Because you know that, a beer, the Red Bull, pop it open, shh, right, CO2. How much CO2 is in the liquid? Well, Henry's law tells you that, so that's where it's useful. So what I'm going to do is we'll take a 10-minute break, and in the next hour, I've got 5 example problems. Homework is a hodgepodge of stuff, and I've got an example